Hi, this is Dan Buller, retired electronics engineer, sitting on the front of my houseboat again. I'm going to continue episode 5 of the series on the Nextest DSP course. Okay, the first one, we have what looks to be a sine wave. It's not. We have what looks to be a sine wave that I created. And let's see, 3 cycles of the wave. So yeah, there's the formula. M is 3. And so we're sampling at 1 megahertz, and 1 megahertz times 3 divided by 512. Get your calculators out. 1 megahertz times 3 divided by 512 is 5.859375 kilohertz. So that waveform is 5.859375 kilohertz. Okay, so now it looks like a sine wave, but guess what? It's not. Should have seen that coming. We do the FFT on it, and you see that we have something in bin 3. That's the fundamental, obviously. And then down around minus 20 dB, we have something in bin 6. That's the second harmonic. And down at minus 40 dB, we have something in bin 9, and that's the third harmonic. So I made this waveform. It's got the fundamental, minus 20 dB of the second harmonic, and minus 40 dB of the third harmonic. And I made that myself. Now let's look at the rest of the wave. We have what appears to be a bunch of noise, but that's at minus, like, below minus 275 dB. So that's mathematical noise. The FFT is generating noise because it does rounding and things when it's doing the FFT. There's a lot of math involved in the FFT, and so what you're seeing there is just mathematical noise. There's no real noise. We're going to pump M up to 9. So M goes up to 9. There's 9 cycles here. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so 1 megahertz times 9 divided by 512. Let's do the math. Get your calculator. Come on, do it. 17.578125 kilohertz. So that's the frequency. So what's happening here is we're taking the frequency of the waveform up, and the M is going up. When we do the FFT on it, we see that the fundamental ends up in bin 9, duh. The second harmonic ends up in bin 18, that's 2 times 9. And the third harmonic ends up in bin 27. That's 3 times 9. What's the Fourier frequency here? The Fourier frequency is the sample rate divided by n. Notice that the sample rate in this series never changes, and so it's always this value. So that equals, do the math, what's 1 megahertz divided by 512? That's 1.953125 kilohertz. So that's the Fourier frequency. That's the resolution of this spectrum. And the F max is equal to Fourier frequency times n over 2, or more simply, much more simply, it's F sub s over 2, or 500 kilohertz. Okay, we bump up M again. Here we make it 21, and so you can count them. There's 1, 2, 3, 4, 5. I won't bore you to death. That's 21 cycles of the wave. 21.0 we're coherently capturing. 21 cycles of the wave, and so we do 1 megahertz times 21 divided by 512. That's 41.015625 kilohertz. Okay, we do the FFT on it. Because M was 21, we know for a fact that the fundamental is in bin 21. You should be able to determine that. The second harmonic is in bin 42, and the third harmonic is in bin 63. Okay, so it's really easy. I mean, you take M, you multiply by 2 for the second harmonic, you multiply by 3 for the third harmonic. And again, the fundamental is 0 dB, the second harmonic is minus 20 dB, and the third harmonic is minus 40 dB. Okay, we bump up M again. We're pushing the frequency up, so there's 51 cycles there, and I won't count them for you. You can count them if you want. Notice there's an interesting undulation here. And you'll say, oh, there's some other signal in there. Wrong, wrong, wrong. Never, never look at the time domain waveform and try to figure out what's going on. When you first looked at this waveform, you had no idea there was a second and third order harmonic. You had no idea. Those harmonics are not showing up here either. What you're seeing there is just the way the samples fall on the waveform as you sample. So those undulations have nothing to do with the waveform. And I kind of hate to use the word artifact, but they're artifacts. 1 megahertz times 51 divided by 512 gives you a test frequency of 99.609375 kilohertz. So that's a pretty high frequency. And it does look about right. It's about 100 kilohertz because M and N have a factor of 10. So that's a factor of 10 less in the test frequency. And when we do the FFT, this is a pretty picture. You know, it would be great if your FFTs could all look like this. The fundamental is in bin 51, the second harmonic is in bin 102, and the third harmonic is in bin 153. You actually have room for 2 more harmonics if you wanted to do that. Bin 51, bin 102, and 153. Multiplying by 1, by 2, by 3, it's so difficult, you know. We push M up to 85, and again, there's the undulation. It looks like there's some signal in there, but there's not. That's one reason I don't like to use scopes, because scopes can lie to you. Looking in time domain, you can get it. It looks like there's something going on. There's nothing going on. It's just the undulation of the way the samples fall. The samples are falling in weird places, and it makes this undulation, but there's no signal there, none. That has nothing to do with anything. I will show you one later that you can see very clearly what's going on. Okay, 1 megahertz times 85 divided by 512, that's 166.015625 kilohertz. Now that was an interesting one because here fundamental shows up in bin 85, the second harmonic shows up in bin 170, and the third harmonic shows up in bin 255. Oops. Now, what's going to happen if we increase M? That's going to be an issue, isn't it? Because the third harmonic is going to fall off the edge of the earth, and Columbus and his crew will all drown. We push the M up to 87, so we have this undulation going on. It's not really a real thing. Don't worry about that. Don't trust time domain. Don't trust time domain. Trust frequency domain. Okay, so 1 megahertz times 87 divided by 512, do the math, and the test frequency comes out to be 169.921875 kilohertz. Now, this is going to be an issue because we're going to look at the frequency domain measurements, and remember that the third harmonic fell off the edge because we were right at the edge on the last one. So now, the fundamental shows up in bin 87, the second harmonic shows up in bin 174, 2 times 87, and the third harmonic shows up in bin, well, wait a minute, 3 times 87 is 261, so that's not 261, that is not 261. Our frequencies end at bin 256, so that is not 261. That's an alias. So this is the way things work. There's the Nyquist band, and bin 87 and bin 174 are inside the Nyquist band, but bin 261 is not. The Nyquist band only goes up to f sub s over 2 or n over 2, and we notice that our last waveform, the third harmonic would have fallen outside of n over 2 or outside of f sub s over 2. Now, we said that 3 times 87 is 261. So there's bin 261. That's the real frequency. The aliasing side, we've got the image of the fundamental. 87 bins down from N. And 87 bins down from that, we have the second harmonic image. And And then 87 bins down from that, we have the image of the third harmonic. Now, that shows up in bin 251. How do we know that? Because we use Dan's aliasing rule number 2. If bin is greater than n over 2, bin equals n minus bin. So what's 512 minus 261? 251. So that's how we figure it out. Now, that was Dan's aliasing rule number 2, but there's another one, isn't there? Okay, so let's go back to the previous page. The third harmonic is pretending to be what? If it's been 251, that's 251 times the Fourier frequency. We did that math earlier, and that comes out to be 490.234375 kilohertz. That's not the right frequency for the third harmonic. The third harmonic is actually up in bin 261. This is the alias of the third harmonic. So that's just the way it works. Okay, that was Dan's aliasing rule number 2. I had to name it because of people were trying to steal it. I told a story in my book. I caught a friend of mine teaching this to the people at Schlumberger, but he didn't mention my name at all. These are rules that I figured out. I came up with them myself, and nobody else taught them to me. And he was teaching them to other people without mentioning my name. And I'm like, hey, what's going on? You know, you're supposed to like tell people that I figured that out. Well, it's public domain stuff since you told me and didn't make me sign a non-disclosure. So I didn't make him sign a non-disclosure, huh? Well, I should have done that, I guess. Here's the way it works. Aliasing can come from anywhere up to light, actually up to cosmic rays, as high as you can go in frequency. And so the only thing you can see is that grayed out portion there between DC and F sub S over 2. That's the Nyquist band. Anything above that can fall into the Nyquist band. It'll fold back and eventually fall into the Nyquist band. That's one reason why you use an anti-aliasing filter. If you have a really high bandwidth digitizer, those things can fall back into the Nyquist band and pollute the Nyquist band. Make it hard for you to see what you're looking for. So what we do is we apply a low-pass filter to the Nyquist band to make sure that those higher frequencies don't end up in there. But you don't really need it. It's only if you don't know what you're looking for. And I tend to not use filters. I really do. Okay, let's look at Dan's aliasing rule number 1. We looked at number 2 before. If bin is greater than n, bin equals bin modulo n. Everybody knows the modulo thing, right? So we'll talk about it as time goes on, but let's say 6 modulo 2 is 0. 7 modulo 2 is 1. 8 modulo 2 is 0. 9 modulo 2 is 1. You see where I'm going? Okay, so we're going to use the modulo operator. And that's a standard operator in C and C++ and Pascal and all those. Okay, Dan's aliasing rule number 2 you've already seen. If bin is greater than n over 2, bin equals n minus bin. So you have to use both of these. Both of these must happen in this order. That's the way you have to do it. Here we pushed M up to 101, so believe me, there's 101 cycles of the fundamental in this waveform. And again, that really interesting waveform pattern that you see there, that's just an artifact. Don't worry about that. Okay, F sub S is equal to 1 megahertz. M is 101. So 1 megahertz times 101 divided by 512 is 197.265625 kilohertz. So that's a pretty high frequency. And then we do the FFT on it. The fundamental shows up in bin 101. What a shock. The second harmonic shows up in bin 202, 2 times 101. And the third harmonic would show up in bin 303, but we can't get to bin 303. You can't see anything above the Nyquist frequency unless you're using XL. XL lets you look above the Nyquist frequency, but let's not go there right now. Okay, so where the heck did this 303 go? We know we see something in the right place, down here, but what bin is that in? Well, we use Dan's aliasing rules. So apply Dan's aliasing rule. Number 1, is 303 greater than n? No, n is 512. So 303 is not greater than n. Is 303 greater than n over 2? Yes, it is. So 512 minus 303 is 209. So, oh, that's about right. That fits in the right place. So that's the third harmonic, or the alias of the third harmonic showing up in bin 209, because 512 minus 303 is 209. So that's an alias. And you can tell it's an alias because it's right next to the second harmonic. The third harmonic should not be right next to the second harmonic with this kind of spacing. Okay, we push M up to 125. Another interesting looking waveform, but again, just ignore those undulations. That's not really an issue. Okay, 1 megahertz times 125 divided by 512 is 244.140625 kilohertz. So our test frequency is getting pretty high, isn't it? And now we do the FFT. The fundamental shows up, again, it's at 0 dB, shows up at bin 125. The second harmonic shows up at bin 250, because 125 times 2 is 250. And the third harmonic would show up at bin 375, but we can't see bin 375. But there's clearly something popping up over there near the fundamental. So we do the math. The aliasing rules number 1 is that number greater than 512? No, it's not. Okay. Is it greater than n over 2? Yes, it is. So we say 512 minus 375 is equal to 137. So that's bin 137. So that's where the alias goes, bin 137. Okay, this is getting really interesting looking. Here we have 169 cycles of the wave, and it makes this real undulating weird pattern. Again, that's not real. Don't worry about it. There's no signal there that's making that happen. It's the same signal you've seen all along. It's just higher frequencies. Okay, 1 megahertz times 169 divided by 512 comes out to 330.078125 kilohertz. And the fundamental shows up in bin 169, but now the second harmonic, where'd that go? What's 169 times 2? That's 338. Well, 338 we can't see in this plot. So that one's aliasing. Now the second harmonic is aliasing. So, Dan's aliasing rules number 1 doesn't apply because 338 is not greater than 512. Is 338 greater than n over 2? Yes, it is. So, 512 minus 338 is 174. So that guy next to the fundamental is the alias of the second harmonic. That's at bin 174. Now, where did the third harmonic go? That went to bin 507. 169 times 3. Or jet ski. 169 times 3 is 507. 507 is not more than 512. So rule 1 doesn't apply. So 507 is greater than n over 2. So 512 minus 507 is 5. So that guy way back there, that is the alias of the third harmonic. The third harmonic is aliasing all the way back to DC. Okay, we push M up again. M is now 175, so go ahead and count them. There's 175 cycles of the fundamental there. So 1 megahertz times 175 divided by 512 is 341 kilohertz. So if you were sampling 341 kilohertz with a 1 megahertz sample rate, this is what you get. You get something that looks like this. And now we do the FFT on it. Fundamental shows up in bin 175. That other thing is the image of the second harmonic. It's not the second harmonic, it's the image of the second harmonic. Let's find out. 175 times 2 is 350. 350 is not greater than 512. Rule 2, 512 minus 350 comes out to 162. So that's the image of the second harmonic. Now where's the third harmonic? 175 times 3 is 525. 525 is greater than 512. So 525 modulo 512 is 13. So that guy down there at 13, that is the image of the third harmonic. He's actually bounced off of DC. Okay, here's a good one. M is now 191. So believe me, there's 191 cycles of the waveform there. So 1 megahertz times 191 divided by 512 is 373.046875 kilohertz. Remember what our M was. M was 191. So let's see, these things look pretty strange. They're kind of backwards, aren't they? The first one we come across is down around minus 40 dB. The next one we come across is about minus 20 dB. And the next one we come across is at 0 dB. So that's been 191. 191 fits within 0 to 256. The second harmonic, that's not the second harmonic. 2 times 191 is not 130. But if you do Dan's aliasing rules, number 1 and number 2, do the math, you'll find out that that's been 130. And Dan's aliasing rules on the third harmonic, 3 times 131, it's well over 500. So we do rule 1 and rule 2, boom, that's bin 61. That's the alias of the third harmonic. Okay, this is one of my favorites. Remember I told you, you'd be able to see those harmonics if you look at a time domain. This is it. This is, I call this the discus fish. So it looks, you can tell it's not a sine wave. And again, that's the undulations of just sampling a very high frequency with a relatively low sample rate. So we're sampling with an M of 255. So 1 megahertz times 255 divided by 512 is 498.046875 kilohertz. And so when you look at the spectrum, you don't see anything, do you? Or do you? The fundamentals all the way over there have been 255. Remember, we're not using bin 256. That's bin 255. So the fundamental is not yet aliasing. What's that thing next to it? Well, that's not the second harmonic, and that's not the third harmonic. I guarantee you that is the alias of the third harmonic. But let's, wait a minute. What's 255 times 2? 255 times 2 is 510. 510 is not greater than 255, so rule 1 doesn't apply, but it's greater than n over 2. So 255 times 2 is 510. 510 is not greater than 512, but it is greater than 255. So 512 minus 510 is 2. Boom. There's bin 2. That's the alias of the second harmonic. And the next one is the alias of the third harmonic in bin 253. Do the math. Works out just fine. Okay, here we push M up to 515. That's pretty interesting. That's 3 cycles of the wave. What do you know? So F sub S is 1 megahertz times 515 divided by 512 is 1.005859375 megahertz. So we're aliasing, aren't we? Our fundamental is aliasing. We're sampling slower than our frequency that we're testing. So when we do the FFT, the fundamental shows up in bin 3, and the second harmonic shows up in bin 6, and the third harmonic shows up in bin 9. And F sub t is pretending to be 5.8 kilohertz, but it's not 5.8 kilohertz. It's 1 megahertz, a little over 1 megahertz. So we're aliasing the fundamental and the second harmonic and the third harmonic. Now, if you didn't have an anti-aliasing filter in there, all that stuff would be coming back here and we'd be seeing it. So that's Dan's rules. I came up with that sitting in a class at Northern Telecom. This instructor was trying to teach us how things worked, and he had this really complicated thing for coming up with the aliasing frequency, because nobody else could tell me what it was. But his thing was really complicated and convoluted, and I didn't like it. So I thought about it just sitting in the class, and I came up with the answer. And that's Dan's rules. Dan's aliasing rules number 1 and number 2. That was long before I did anything with harmonics. So those are really useful. Now, I used to talk about those. I was one time giving a class for these students, and these 2 guys in the students were actually going to be software engineers, new software engineers for Credence. And so I was telling them a story about Dan's rules, and I said, by the way, this software does not, in the Credence, does not calculate for Dan's rules. So you'll never know how this works. Well, they came up to me on a break and they said, we would like to incorporate Dan's rules into the system software. Can we do that? Is that okay with you? And I'm like, yeah, of course, totally. And so they went back, once they graduated, they went back to their boss and said, we want to code this into the software. And so then Dan's rules got incorporated into the Vista software, and that runs, I mean, I have a friend who's still running Vistas. Steve Winicki runs it. Well, he sold the company for $3 million bucks. That software still runs millions of times a day. So millions of times a day, my code, Dan's rules, run on testers all over the world. That's a really nice thing. Dan's rules, look it up, just type Dan's rules, you'll see it on the web. You don't have to remember it, it's out there. That's how you can calculate where an alias is going to fall. When I was first doing this, I couldn't get anybody to tell me where the aliases would fall. Even Mahoney's book didn't cover it. I figured it out myself. So those are mine. It's called Dan's Rules because I came up with it. Okay? So that's enough for this time. I'm going to get into some other stuff next time. But until then, this is Dan Bullard from the river. See ya.